Our goal with this problem is to graph f of x. We've got a tremendous amount of information here about f prime, f double prime on the intervals from 1 to 2, from 2 to 3, 3 to 4, 4 to 5, 5 to 6. We should start thinking about what's happening on each of these intervals as we're writing this information down. For example, here I know that while f is above the x-axis on its graph, this function is decreasing and also concave down. And over here, I see the function is now below the x-axis. F is now negative, where f prime is negative, so f is still decreasing, and f double prime is positive, so f must be concave up. So what's happening then at x equal to 2, where the graph of f went from being positive y values to negative y values? Well, if we look down here at the second table, we can see that in fact at x equal to 2, the function has a value of 0. The derivative is undefined and the second derivative is undefined, but the function has a value of 0 there. And for us, we understand that to be an x-intercept because here we saw f was going from positive values to negative values. So we were crossing the x-axis at x equals 0. So let's see if we can draw a graph of f of x. I'll start by putting a 1 here. And at 1, we have a value of 4. 1, 4. And as we head to 2, we know we're supposed to be decreasing and concave down. So I'm decreasing and concave down, and I got to that place at x equals 2, where now I'm about to go below the x-axis, but at x equals 2, I have a value of 0. I'm also told here at 2, our slope is going to be undefined. Now, that can mean one of two things. It can mean I have a vertical slope, or it can mean I can't take the derivative at that point because of, say, a corner or cusp where the limit of the slopes of the function aren't the same value from each side of this point. So let's see which of those we're going to have here. As we go from 2 to 3, the function is below the x-axis, is decreasing, and is concave up. And when we get to 3, we're going to have a y value of negative 4, and the slope will be 0. So I think if I'm decreasing and concave up, I'm going to be looking like this. Decreasing and concave up as I go from 2 to 3. And this appears to have been that vertical slope, not anything like a corner or cusp at x equal to 2. Okay? From 3 to 4, I'm still below the x-axis, and this time I'm increasing and concave up, and I get to the point where f is equal to negative 2. Well, at 3, f was equal to negative 4, so negative 3, 4, and this was 2, 0, and I'm going to go to a place over here called x equals 4 that is still only at negative 2. I'm going to be increasing and concave up. But at 3, the slope should be 0. And so I think I'm just going to have something that looks like that. Horizontal tangent here at 3, then increasing and concave up from 3 to 4. Now, at 4, I see not only do I have a y value of negative 2, so 4, negative 2 here, but I also recognize that the derivative is undefined at this point. And again, I'm not sure why the derivative is undefined, but hopefully when I look at the next interval, that will become apparent. So from 4 to 5, the function is still below the x-axis. The function is decreasing and concave up. Well, wait a minute. How am I going to draw decreasing and concave up here? Decreasing and concave up looks like, oh, that's why the derivative is undefined at 4. Because I have this corner. Maybe it's even a cusp? No. Well, the slope is undefined. And that's the definition of cusp. So I have an undefined slope here. and decreasing and concave up between 4 and 5. And when I get to 5, my slope, my f prime, should be 0. So just like at 3, I should have a minimum, a flat spot with a horizontal tangent when I get to 5. So let's put 5 on our list here and draw to that. Okay, decreasing and concave up. And now what do we have? We have a y value of -6 here. So that's 5, -6 we're thinking about. And from 5 to 6, the function is still below the x-axis, this time increasing and concave up. Increasing and concave up until I get to a y value at 6 of 0. Y value of 6 at 6 of 0. So we're increasing and concave up from the point at 5, -6 until we get to the point at 6 where we have a y value of 0. I notice also here that the slope is going to be undefined and the second derivative undefined. And after 6, I notice that now the function is going to continue to be negative. So I'm not going to go across the x-axis. I'm going to stay below. I'm going to be decreasing, and I'm going to be concave down. So if I draw decreasing and concave down at this point, that looks like this. All right, so I think that's our graph of continuous f of x on the interval from 1 to, after 6. I hope this was helpful. Let's take a look at another problem I have for you. This one is reminiscent of the one that Megan asked on the group me on Saturday night. It's a great test question. We're given a graph here of, I believe this was f prime of x. No, this is a graph of f of x. I'm sorry. This is f of x. And we're asked, when do f and f prime have the same sign? So f and f prime have the same sign. Well, I know here at A, f is above the x-axis, so f is positive, and I know that f prime would be positive because this function is increasing. So I think at x equals f, not x equals a, we have the same sign. I'm not sure what the slope is here. It kind of looks infinite at that point, and infinite doesn't equal 0, so I'm thinking that that is not something that's going to be helpful for me. One thing that might be helpful for me in doing this problem, though, is rather than trying to ask at each point all these different questions, it might be worth the time to draw a little graphic organizer and to gather all that information first about f, f prime, and f double prime at each of these places. And we're concerned about A, B, C. Probably don't need me narrating these letters. And a remarkably wide spot for F. Okay, so, and there's an H and J. Well, I guess I do need that space. H and J. Okay. At A, we know the value is 0. We think that f prime would be positive. And we think that f double prime, this looks concave down here, would be negative. And at B, it looks like f is positive. It looks like f prime, I have a horizontal tangent there, f prime would be 0. And f double prime, well, I'm still concave down on f, so still negative. Okay, what about at C? C looks like an inflection point as well as an x-intercept to me, where I'm changing from concave down to concave up. So I think f double prime is going to be 0 and f is 0, but this function is decreasing on this interval and at that point. So I'm going to have f prime be negative. At D, I think I have another zero slope. F is clearly below the x-axis, and this function is concave up at D, so f double prime would be positive. Again, D is below the x-axis, so f is negative. D is with a horizontal tangent, so f prime is 0, and at D, f is concave up, and so we have positive second derivative. At E, I think I have a positive zero first derivative as well as a zero function value. So f is equal to 0 and the slope is equal to 0 at that point, but the function is concave down here. Okay, now we go back to f. What can we say about f? We can say that at f, this function is above the x-axis, so positive. We can say the function is increasing here, so positive, and concave down, so negative. At h, we're below the x-axis, we are decreasing, and we are concave up. And finally, at I, we're below the x-axis, we're decreasing, and we're concave down. Well, look, a place where we have all three have the same sign. So now when I go back over here and look at f and f prime have the same sign, well, it's really easy to read that off of this chart. I see that f and f prime seem to have the same sign at E, at F, at H, and at J. Those would be places where f and f prime have the same sign. What about f and f double prime have the same sign? Oh wait, we'll fill this in. This was f and f prime have the same sign at E, F, H, and J. Okay, f and f double prime have the same sign. So I'm looking at this row and this row. No, ooh, at C. No, oh, and at J. Now, f prime and f double prime have the same sign. No. Whoa, only at that one place, J. And then finally, we want f and f prime equal to 0, and we saw that at point E. Are there any places where f prime and f double prime are both equal to 0? I don't see that here. What would we be seeing on the graph at a place where the first derivative was 0 and the second derivative was 0? Well, I think we would probably be looking at a place where there might be an inflection point. We would also be looking at a place where there was a 0 slope. And so we're thinking about something like this, which our graph doesn't have. Okay, well, there's our second problem. Answering these questions, and I find using this graphic organizer terribly helpful. Certainly always worth my time to do it. Now something a little more intense, or at least a little more time consuming. We've got a graph of f prime given to us. It's always important to note what function you're looking at, and here we're looking at a function of f prime. And we're asked when f is increasing. Well, if f is increasing, what do we know about f prime? If f is increasing, then f prime is greater than 0. Oh, well, I can read that off this graph. F prime is greater than 0 from A to C. And when is f decreasing? F is decreasing means f has negative slopes. And if f has negative slopes, then f prime would be below the x-axis on f prime. So that seems to happen from C to F and after F. So I think here I'm going to say C to F union F to infinity. Okay, when does f have a max? Well, f has a max when f goes from increasing to decreasing, or when f prime goes from positive to negative. So at this point, at point x equal to c, I think that f of x has a max. Now, this is an endpoint, and I should definitely be considering endpoints from this point where I have a zero slope. The function f is increasing. So if I'm at a point and the function is increasing, that's not going to be a max, that's going to be a min. So I'm going to put an A there for later. What about here? Do I have a min or a max? Well, f is decreasing because f is negative to the left of that point, and f is decreasing after that point. And so I think I have something that looks more like decreasing at f, where I have a zero slope there briefly, but no max or min. And down here, well, I'm going to go with an arrow there, and so I'm going to say there's no endpoint there. There's only this endpoint here to concern myself with. So C appears to be my max, and I have a min at A. Okay, let's go further. F prime increasing. Well, now they're asking me about F prime, and that's actually the graph that I'm looking at. So I'm going to look at the graph and ask, when is the graph that I'm looking at increasing? And that graph seems to be increasing from A to B. Are there any other places where this graph is increasing? Well, decreasing. Oh, increasing from D to F. Union D to F. And when is this function decreasing? Well, this function is decreasing from B to D and from F on. So B to D, union F to infinity. Okay, I'm going to fold this up so that we have some more space. Now we want to know when F prime has a max. Not F has a max, but F prime has a max. And f prime is the graph we're looking at. It has a max at B. It also has a relative max at F. And f prime has a min. Well, f prime has a min here at A, and also a min here at D. Now, f double prime positive. F double prime positive happens when the slopes of f prime, the slopes of this graph, are positive, which means whenever I thought that f prime was increasing, f double prime is going to be positive. And we said that f prime would be increasing on A to B, union D to F. This is when f prime has positive slopes. This is when f prime has positive slopes. So those are places where f double prime would be positive. Now we're asked about f double prime being negative, and f double prime is negative when f prime is decreasing. And we said f prime would be decreasing from B to D and from F on. So B to D, union F to infinity. Now, when is f concave up? Well, f is concave up when f double prime is positive. So we know that's going to be at A to B, union D to F. And when is f concave down? Well, that's going to be when f double prime is negative. And so that's from B to D, union F to infinity. What about f having an inflection point? An inflection point on f. We want to know when f double prime goes from positive to negative. That seems to happen at B. Or from negative to positive. That seems to happen to D at D. So I would claim both of those, B and D, as inflection points on f. What about at f? Well, at F, we see that, um, oh, at F, we see that um, we've gone from F double prime is negative to F double prime is positive, and so that means we also have an inflection point there. Many people want to say something about this point. Um, this point is an inflection point on F prime, but that would only be a zero on F triple prime. It might be a max on F double prime, but no one's asking me about maxes and mins on F double prime. So for my purposes, this is a red herring point. It doesn't provide any information for me in this problem. But I'm able to determine, given f prime of x, all this information about f of x, f prime of x, and f double prime of x simply by using f prime of x. Again, f is increasing when f prime is above the x-axis, so from A to C. F is decreasing when f prime is below the x-axis, so that's everywhere here except at f, where we have f prime equal to 0, which is why I did from C to F union F to infinity. Remember, this infinity is going this way, not this way. Then F has a max when F prime goes from negative to positive. I'm sorry, from positive to negative. That's here. F prime is going from F is going from increasing to decreasing, so F prime is going from positive to negative. And that tells me that F has a maximum. Here I have no sign change in F prime. F prime is negative to the left of x equals F and negative to the right of x equals F. So I don't have a minimum or maximum on F of x at that point. But we did mention over here that we had an endpoint, a left endpoint, and from here, f prime is positive means f is increasing from that point. And so if I'm increasing from that point, then I know that f must be have a minimum there at that point. Okay, whether I'm increasing concave up, concave down, or in a constant manner, the fact that f is increasing after this point tells me that this point is a minimum. All right, then we talked about f prime, the given graph, and it was easier to read things about f prime here. Generally, what I find is a little cognitive dissonance switching my brain from thinking about a graph that I'm not looking at. Namely, I've got information here on f prime, and I'm using it to think about f, which is not shown, now to thinking about the graph that is shown. But it's easy enough for me to say, okay, I'm looking at this graph and I'm being asked about this graph. When is this graph increasing? This graph increases from A to B. This graph decreases from B to D. And this graph increases from D to F. And this graph decreases from F to infinity. We see that f prime has a max over here, has a max over here, and has mins here and here. It's much easier, I find, to read f prime information off of the f prime graph than to go backwards or forwards and talk about f or f double prime. But with more practice, we'll get more comfortable with that. So as we think about f double prime here, f double prime is positive when f prime is increasing, and f double prime is negative when f prime is decreasing. So all I'm doing is importing this information down here, and this information down here. And likewise, when is f concave up? Well, that's when f double prime is positive again. And when is f concave down? Well, that's when f double prime is negative, or when f prime is decreasing. And remember, we can have an inflection point where f double prime changes sign. We see f double prime going from positive to negative at B, going from negative to positive at D, and going from negative to positive at F. And so we have 3 inflection points here. where f double prime changes sign. Okay, well, that's that problem. Let's see what we have next. Okay. So I thought this would be a nice by-hand do-everything problem where we're given an f of x and no calculator. And we're asked to find maxes and mins and increasing and decreasing and concave up and inflection points. So let's get about doing this. We're going to need some information. We're going to need to know about f prime. So we'll make an f prime. We'll take the derivative here. We'll get 1. The derivative of sine x is cosine 2x. Don't forget chain rule here, times 2. And when is f prime equal to 0? Well, that happens when negative 1/2 equals cosine 2x. Ooh, this is a little tricky. So cosine is equal to negative 1/2 at 2 pi over 3 and 4 pi over 3. But if I'm thinking about this on, let's have 0 to 2 pi, just to make our lives a little more humane, I need to go around the unit circle twice picking up solutions. And so I'm going to have 8 pi over 3 and 10 pi over 3 as well. These are places where cosine is equal to negative 1/2. But that would get me 2x, and I'm interested to know about x. And so that would be 2 pi over 6, 4 pi over 6, 8 pi over 6, and 10 pi over 6. Or pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. Okay? So here I have places where f prime is equal to 0. If I make an f prime sign chart now and plug 0 and 2 pi on, as well as my critical points, pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3, I want to test these intervals with f prime. Something in between 0 and pi over 3. I don't know, how about pi over 4? If I plug a pi over 4 in here, 2 times pi over 4 is pi over 2. The cosine of pi over 2 is 0. 0 times 2 is 0, plus 1 is positive. If I put in something over here between pi over 3 and 2 pi over 3, like pi over 2, pi over 2 times 2 is pi. The cosine of pi is negative 1. Negative 1 times 2 is negative 2. Negative 2 plus 1 is negative 1. Okay. What about something in between 2 pi over 3 and 4 pi over 3? Well, pi is between those two, and that's pretty easy to work with, so let's plug in pi for x. So 2 times pi is 2 pi. The cosine of 2 pi is 1. 1 times 2 is 2. 2 plus 1 is 3. So we get positive here. Something between 4 pi over 3 and 5 pi over 3. Well, that's between this third quadrant angle and this fourth quadrant angle. I'm thinking about 3 pi over 2. 3 pi over 2 times 2 is 3 pi. The cosine of 3 pi is negative 1. Negative 1 times 2 is negative 2. And negative 2 plus 1 is negative 1. And what about between 5 pi over 3 and 2 pi? I'm going to go with 7 pi over 4. So 7 pi over 4 times 2 is 7 pi over 2. Now, 7 pi over 2, well, let's think about that. There's 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, 5 pi over 2, 6 pi over 2. 7 pi over 2 looks like 3 pi over 2. So the cosine of 3 pi over 2 is 0. 0 times 2 is 0, plus 1 is 1. Okay, so this is a sign chart right now for f prime that takes into consideration all the places where f prime was equal to 0. But you know, we didn't talk about other places we could have maxes and mins, namely places where f prime was undefined. Well, I didn't think about that here because our f prime is primarily made up of a cosine function, and cosine is defined everywhere. Multiplying those values by 2 and then adding 1 stretches them vertically and pushes them up 1, but doesn't make undefinedness. So I think f prime is defined everywhere. And we do have, as a late arrival, a bounded interval. And so we do want to think about the locations of maxes and mins at being at those endpoints. And since we filled in our sign chart, why don't we do that part now? What sort of event do we have on f of x if f prime of x is positive to the right of x equals 0, and this is our left endpoint? Well, this means that the function f is increasing after this point, and if I'm increasing after this point, then I must have a min at x equals 0. Don't forget to write the justification sentence for that left endpoint min. And let me know if you need me to go over any of those justification sentences, including the justifications for endpoints. Okay, then we've got another min here at 2 pi over 3, where f prime goes from negative to positive, and another min where f prime goes from negative to positive at 5 pi over 3. So we have mins at 0, 2 pi over 3, and 5 pi over 3. What about maxes? Well, there's a max where f prime goes from positive to negative, where f prime goes from positive to negative, so I know at x equals pi over 3 and 4 pi over 3, f would have maximums. But what about this endpoint at 2 pi? Don't forget about that. F, because f prime is positive here, f is increasing until we get to that endpoint at 2 pi. Therefore, the endpoint of 2 pi is also and x equals 2 pi, a max. Remember, we're going to write a separate justification sentence for each of these. We should really be in that habit. The justification for this is not the same as the justification for these. In a pinch, you could get away with a well-worded one justification sentence for both of these, but you couldn't use one that covers all three of these points. So be in the habit of writing justification sentences for all the points. What else do we need to know? We need to know when f is increasing. And f is increasing whenever f prime is positive, and that happens on 0 to pi over 3, union 2 pi over 3 to 4 pi over 3, union 5 pi over 3 to 2 pi. And when is f decreasing? When f prime is negative. F prime is negative on these intervals, so on pi over 3 to 2 pi over 3, union 4 pi over 3 to 5 pi over 3. These are places where f prime is negative, therefore f is decreasing. Okay, so now we need to talk about concave up, concave down on f, as well as inflection points on f. And I can do that from when f prime is increasing, but from this information I don't know when f prime is increasing or decreasing. I just know that f prime is positive or negative. So given my f prime of x, remember that f prime of x was 1 plus 2 cosine 2x. We need to find f double prime of x. So let's find f double prime. Please don't forget to take the derivative of this. So many students forget that. The derivative of 1 is 0, and so that's gone from our second derivative. Now the derivative over here of 2 cosine 2x would be negative 2 sine 2x. Don't forget the derivative of the inside function times 2, or negative 4 sine 2x. And we're looking for critical points on f double prime. Remember, we can't have inflection points at endpoints, so we're not worried about that here. But we do want to know when f double prime is 0 or when f double prime is undefined. But our f double prime is Sine. Sine is defined everywhere. So f double prime will never be undefined. And we don't have to worry about endpoints for inflection points. So all we need to do is figure out when f double prime equals 0. And so that happens when negative 4 sine 2x equals 0. And that's when 0 equals sine 2x if I divide both sides by negative 4. And so really I'm asking the question, when is sine equal to 0? But I'm going to go around the unit circle twice, picking up solutions on 0 to 2 pi. So the first time would be at 0. The second time would be at pi. The third time would be at 2 pi. The fourth time would be at 3 pi. And because 2 pi is included, I've got to go that full circle around and get 4 pi here. Okay, so this is not what x equals, though. This is what 2x equals. So x is going to be 0, pi over 2, pi, 3 pi over 2, and 2 pi. Well, we know that we can't have inflection points at endpoints. So I'm not worried about those. So on my f double prime sine chart, which I'll put down here, I can put my 0 and 2 pi. But I'm really concerned about pi over 2, pi, and 3 pi over 2. Okay, and I'm testing values in f double prime. So one of the reasons I write this down here is to remind me of, this is an f double prime sine chart, therefore I'm plugging values not back into f prime or f, but instead plugging values into f double prime. So what's something between 0 and pi over 2? How about pi over 4? And if I do pi over 4 times 2, I get pi over 2. And the sine of pi over 2 is 1. 1 times negative 4 is a negative. Something between pi over 2 and pi could be 3 pi over 4. So 3 pi over 4 times 2 would be 3 pi over 2. The sine of 3 pi over 2 is negative 1 times negative 4. I get a positive second derivative there. Something between pi and 3 pi over 2. How about 5 pi over 4? 5 pi over 4 divided by 2 is 5 pi over 2's. And if I'm thinking about 5 pi over 2's, there's 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2. 5 pi over 2 looks like pi over 2. The sine of pi over 2 is 1. 1 times negative 4 is a negative. And then finally, something between 3 pi over 2 and 2 pi. I'm going to plug in 7 pi over 4. 7 pi over 4 times 2 would be 7 pi over 2, which we said earlier looks like 3 pi over 2. The sine of 3 pi over 2 is negative 1. Negative 1 times negative 4 is positive. So I see then, based on this sine chart, that f is concave up on this interval and this interval because f double prime is greater than 0. So we're looking pi over 2 to pi, union 3 pi over 2 to 2 pi. And f is concave down when f double prime is negative, so on this interval and this interval, which would be on 0 to pi over 2, union pi to 3 pi over 2. And then inflection points. Well, I'm looking for sign changes on f prime, and I've got 3 of those. So inflection points, not on f prime, not on f double prime, but on f would occur at x equals pi over 2, pi, and 3 pi over 2. Remember, we can't have inflection points at endpoints because endpoints don't allow anything to occur after that point, and an inflection point is a place where we're changing concavity. Say, in this case, from concave up to we'd want to see concave down on the other side. We don't have anything on the other side of this because 2 pi is an endpoint. Okay, so that's a lot of information. I might want to point out that these inflection points on f, these places where f double prime changes sign, are also places on f prime if we had a graph of f prime, where f prime has a minimum, because f prime is going from decreasing to increasing, decreasing to increasing, so f prime has a minimum. Remember, f double prime represents the slopes of f prime. So I know that f prime is decreasing, I know that f prime is increasing, I know that f prime is decreasing. As f prime goes from increasing to decreasing at pi, f prime would have a max on it. That max became a 0 on f double prime with a sign change and therefore an inflection point on f. I also notice here at 3 pi over 2 where f prime would be going from decreasing to increasing, a minimum on f prime. So don't forget you've got that information here as well. Okay, that's that problem. And I'm on to the last problem now. And this last problem is a mean value theorem problem. And we want to consider two things. First, do we meet the preconditions? We should always think about the preconditions. Remember, preconditions say f is continuous on the closed interval and f is differentiable on the open interval. So we have to consider both of those things. And a lot of times when we see like our f of x, something in a denominator, we think, uh-oh, that's not going to be equal to 0. But let's look again. Will x squared plus 4 ever be equal to 0? Well, if I subtract 4 and take the square root, I'm taking the square root of a negative number, and that doesn't make any sense. That's not going to ever occur in our real number graphs. And if I think about this graphically, I'm thinking about the graph of a parabola shifted up 4 and wondering, does this parabola ever cross the x-axis? And the answer is no, it's shifted up 4. This parabola will never cross the x-axis. So I know that this function then, since the only thing we were worried about was a 0 in the denominator, this function will be continuous on this interval. In fact, this function is continuous for all real numbers. So we've met that precondition. But what about differentiable on 1 to 4? Well, for that, we're going to need to find f prime. And I don't want to do f prime with the quotient rule. I want to rewrite f as x squared plus 4 to the negative 1 times x, and I want to use the product rule. So f prime then is going to be 1 times x squared plus 4 to the negative 1 plus x times negative 1, x squared plus 4 to the negative 2. And please don't forget to take the derivative of that inside function. You need to go back and take that derivative of that inside function. So we need 2x here. Okay, so what are we going to factor out? Well, we've got x squared plus 4 in each of these. So I'm going to factor out from my f prime an x squared plus 4 to the smallest power, negative 2. And what's going to be left? Well, when I factor a negative 2 out of here, I'm going to be left with positive 1. So this is x squared plus 4 to the 1. Now I have my plus sign, and then I've got this negative, this x, we took out all of this, and this 2x. So that's going to be minus 2x squared. Well, I guess I can tidy that up a bit to be x squared plus 4 to the negative 2, and then negative 2x squared plus 1x squared is negative x squared, or 4 minus x squared. Okay, so I have a derivative. Does this derivative exist everywhere? Well, if I rewrite this as x squared plus 4 squared in the denominator and 4 minus x squared up top, this parabola exists everywhere, and this, we said x squared plus 4 is going to exist everywhere. So this derivative is definitely differentiable on 1 to 4. So we're good to go. Now we're ready for satisfying our curiosity about the location of C, by which I mean, remember the mean value theorem guarantees us at least one point called x equals C, where f prime at that x value is equal to f of b minus f of a over b minus a. So I'm thinking I need to do this part first. I need to find f of 4 minus f of 1 over 4 minus 1. Well, f of 4 requires me, oh, you didn't see that, sorry. F of 4 requires me to plug a 4 into the original function, and f of 1 requires me to plug a 4 into the original function. So I think I'm going to fold this down so I can see the original function while I do this. Okay, so if I plug a 4 in down here, I get 16 plus 4 is 20. If I plug a 4 in here, I have 4 over 20, or 1 over 5. If I plug a 1 in for each of these x's, I get 1 over 1 plus 4, 1 over 5. Oh, look at that. I end up with a 0 slope. So we're wondering where f prime equals 0. Now, many students get to this part in the problem and they say x equals 0 is the answer because they feel like they've done enough work and surely it must be done. But remember, the mean value theorem says that this average rate of change, in our case 0, has to be equal to the instantaneous rate of change at least some point, x equals c. That's what we're trying to find. So we want to set our derivative. Remember, our derivative was x squared plus 4 to the negative 2 times 4 minus x squared. We want to set this derivative equal to 0. Well, when is that derivative equal to 0? This denominator is never equal to 0, but this numerator is, and for what I mean by denominator and numerator, just rewrite it with no negative exponent. So I'm wondering when this equals 0. If I multiply both sides by x squared plus 4 squared, over here these cancel, and 0 times this stuff is still 0. So the denominator plays no role in finding when this derivative is equal to 0, only the numerator. So let's take a look then over here. When is 4 minus x squared equal to 0? That's 4 equal to x squared. So x equals plus and minus 2. Oh, but wait a minute here. Don't we see this restriction? We're only concerned about c values that live on the interval from 1 to 4. Negative 2 is not on 1 to 4, so we have to be smart enough and aware enough and attentive enough to throw that away and say that our only solution is x equals x equals 2. At x equals 2, the slope of the secant and the slope of the tangent have the same slope. All right, well, I hope this was helpful reviewing an MPT problem as well as all these other problems. If there's anything else I can do, please let me know, and I'll try and make a video of those. Otherwise, have a great day.